I'm Alex Hom, the presenter of this paper, Hierarchical Probabilistic Ultrasound Image Inpainting via Variational Inference. So why are we doing Inpainting? Because there are several potential applications of this work. For example, we can use Inpainting to remove artifacts. We can use it to do some sort of anomaly detection or to fill in unclear regions to help downstream algorithms. I'll go over these in the experiment section. Another quick question is why we want to use variational inference instead of a deterministic one. Think about how expert would do the job. They will consider the correct semantic meaning, like is it an organ or is it just background or is it something else? And then fill in the regions with the correct noise pattern since ultrasound is very noisy. They also will consider the continuity of the boundaries of such regions. The semantic information would be the same amount expert, but the details and the noise and the boundaries would be different. Here is an overview of our proposed model where these are the latent variables and these are the compressed representation of the latent variable. X is the masked image and Y is the original image, where both X and Y are seen during training, but only X is seen in inference. During learning, we learn in priors and in posteriors by maximizing the elbow. During inference, the masked image X is observed, so we make the prediction only using the priors. In terms of the training objectives, we divided the training objectives into 4 parts: the reconstruction loss, the perceptual loss, the style loss, and the KL divergence. The reconstruction loss is designed to have the predicted image match the original image, but we actually don't want it to match perfectly either. So because we want some variance in the output. So we use a Laplacian pyramid loss to give higher weights to the low frequency information. Besides, we also assign low weights to the pixels that are further away from the scene regions. For style and perceptual loss, they're commonly used in the style transfer setting. It is used here so the network can learn to generate the correct semantic information texture. At last, the KL divergence should be used to minimize, minimized to maximize the elbow. So for more information, please refer to the paper. We implemented the proposed model in the neural network shown on the slide, where the blue blocks are normal convolution blocks, and the yellow and green ones are the dilated convolution. There is a prior network and also a posterior network, and both of them are trained during learning, but only prior network is used in inference. Each conv block consists of the structure on the right. So let's look at some experimental results. This is the result on the live pig. So we randomly sample from the latent space to generate multiple plausible results. All the results look kind of plausible, but there are like some differences in the details. Let me play a video real quick to show to better show what I'm saying. So here's some video of like results. Like in this part, and here are the Inpainting regions. They all look kind of plausible, but they kind of differ in the fine details. Okay, so we're also comparing our results against like results from other methods. So TALIA is a non-learning based method. DF stands for diffusion and PCOM stands for partial convolution. These two without L2 means that they're using our training objective. And these two with L2 means they're using an L2 loss. And the HPI WOBI means HPI without variational inference. So both visually and number-wise, our method is clearly better than the other methods. We also apply a reverberation artifact segmentation algorithm to segment the artifacts, and after segmenting them, we use the Inpainting algorithm to fill in the regions to remove such artifacts. Therefore, we train our Inpainting algorithm on images without artifacts and test them on the artifacts. The qualitative results shown that our methods does a better job like removing such artifacts as well. And last, let's take a look at some applications on needle tracking. So we select the painted regions by the following steps. In our previous needle tracking paper, we use an intensity thresholding and a Sobel filter response thresholding to select the candidate points for weighted Rensek fitting. First, we ran both thresholding methods in the bounding box of the ground truth labels of the needles to select the candidate pixels for weighted Rensek fitting. We then search along the label needle axis and detect the boxes where there are no candidate points and inpaint the regions inside the box. We later evaluate the results with tip and shaft error. The tip error is the difference in location between the detected and the labeled tip, and the shaft error is the mean absolute error of the pixels on the polynomial of the labeled needle to the detected needle. The results are shown in the table, and it shows that our Inpainting algorithm can help the tracking. Here's a quick example of the needle tracking. So the left one is the result, like based on Inpainting, and the middle one is without Inpainting, and the right one is the ground truth. So it's pretty clear that our method improved the results of needle tracking. And that's it for our work. Thanks for listening.